Good morning and good evening, everyone. I'm Jinfeng Zhang, a researcher from Recon AIP. Today, I'm going to host the third TrustML Young Scientist, hold the fifth TrustML Young Scientist seminar. Before that, allow me to briefly introduce the Recon AIP to our valuable guest. The full name of Recon AIP is the Recon Center for Advanced Intelligence Project. AIP was founded in 2016 as the research center for the Max AIP project. AIP Center conducts Japan's leading AI research, which is headed by Professor Sugiyama. AIP aims to enhance the AI's fundamental technology and its real-world applications. AIP encourages the collaboration with various researchers and engineers in the related fields. We would be grateful if you could visit us in our Nihonbashi office in Tokyo in near future. All right. Hi, Tian. Can you able to share your screen?
Let me share my screen.
Yeah.
Okay.
Okay, then I will introduce you. Today, our first guest is Tian Li from Carnegie Mellon University. Tian Li is a PhD student in the computer science department at Carnegie Mellon University, working with Virginia Smith. Her research interests are in distributed optimization, federated learning, data-intensive system. Prior to CMU, she received her undergrad degrees in computer science and economics from Peking University. Let's sincerely welcome Tian Li to give her talk, Fair or Robust, addressing competing constraints with personalized federated learning. Hi, Tian, you can get started. Thank you for your coming. Great.
Yeah, thanks for having me here and thanks for the introduction. So hi everyone. Today I'm going to talk about some of our works on federated learning. So specifically on fair and robust federated learning with personalization. And this is joint work with Shenyuan, Amat, and my advisor, Virginia. So first, I would like to just briefly give some background on federated learning. So federated learning is privacy-preserving training in heterogeneous and potentially massive networks. So those networks can be a network comprised of thousands to millions of edge devices like cell phones, or it can be a network of isolated organizations such as hospitals. And people usually call the first case cross-device settings and the second case cross-silo settings. And so jointly training statistical models in these networks have many potential applications, like you can imagine, can do anomaly detection in IoT devices, or adapting to pedestrian behavior or autonomous vehicles, providing personalized healthcare on wearable devices, and performing predictive maintenance in sensor networks deployed in industrial machines. And federated learning has also shown great promise in various applications deployed at the edge and also in healthcare and finance services. So what does the workflow look like and what are the unique challenges in federated learning? A typical objective, like the optimization objective for federated learning, is to find a global model W to minimize such a loss function, which is a weighted average of the local loss on each device. And capital Fk is the empirical loss on device K, and Pk is some predefined weight. For example, we can set this pk to be the fraction of samples of this device. And we assume that we are in a typical centralized training setup in this talk. So there is a central server and a bunch of devices or organizations communicating intermediate information with this central server periodically to learn a good global model. And so there exists a bunch of unique challenges here, and I'll mention some of the major ones. So first, the entire systems are heterogeneous due to the variable hardware of the devices and the network conditions and so on. The user data generated from each device are non-identically distributed. So they're not coming from the same global distribution. And this issue, which we call statistical heterogeneity, can affect the training pipeline a lot. And also communication is extremely expensive in such settings compared with traditional distributed machine learning in data centers, because those devices are connected potentially in a wireless way, right? And lastly, privacy is also a big concern. So federated learning keeps all the data, all the user data local, which is a first step towards protecting user privacy by hiding all the data. But transmitting intermediate information, such as some parameters, can still reveal sensitive user information. And there are many interesting questions we can ask in this space, and some of them have been extensively explored in recent works. And in this talk, I would like to first talk about fairness in federated learning from a representation bias point of view. So because the devices are massive and heterogeneous, it's very likely that fitting a global model to all of them will disadvantage a subset of the devices. So a natural question we ask is, can we equalize performance across diverse networks? And just as mentioned before, typically the federated objective is simply this traditional empirical risk minimization, where we just minimize this empirical average loss. But minimizing such an aggregate function can disproportionately advantage or disadvantage the performance on some devices, and there are no accuracy guarantees for individual devices. So for example, here we show the test accuracy distribution of all devices from a model trained in the real-world federated dataset, and can see that a small group of the devices suffer from low test accuracy. So can we encourage more fair model performance across devices? And the fairness definition considered in this work is the uniformity of the performance distributions. And our goal is to reduce the performance variance by increasing the performance on the worst performing group of devices while maintaining the original good average accuracy performance. So we propose a fair objective for federated learning, and it's called Q-fair federated learning, or QFFL. So this objective minimizes an aggregate row-weighted loss parameterized by this hyperparameter Q, such that the devices with higher loss are given higher relative weight. This objective is inspired by alpha fairness for fair resource allocation in wireless networks, and it enables flexible fairness accuracy trade-offs through this tunable hyperparameter Q. So when Q is equal to 0, this objective recovers the previous objective, ERM objective. And when Q is large enough, like when Q is close to positive infinity, and it reduces to the classic minimax fairness, where the goal is to just minimize the loss of the worst performing device. And compared to minimax fairness, and this objective is more desirable in certain cases in terms of both the computation efficiency and the properties of the final solutions. So theoretically, we have some generalization guarantees for QFFL, and the generalization bound recovers the known case of the generalization for this minimax case. And we define various uniformity metrics, including the variance and the entropy of the loss distribution. And we show that increasing Q results in more uniform performance distribution across the devices. So empirically, going back to the previous example, the model, so in the baseline, the model can fail on some devices. And by using QFFL, we can maintain the same overall average accuracy while reducing the variance. So the performance of the worst performing device has improved at the cost of potentially reducing the best accuracies a little bit. So here are the main empirical results. So on these 4 federated data sets, so the first one is a synthetic one, and the other 3 are federated data sets. By using QFFL, which is red shown here, the performance distribution is more centered. So, and on average, it can roughly cut the variance by a half. So beside fair federated learning, this general trade-off between average and minimax case can also be possibly applied to the to other settings such as meta learning. And So how do we solve this objective in large-scale federated learning? So this, I'll just very briefly mention this part and leave the details, not to talk about the details. So generally, we identify the two challenges here. And first, in order to trade fairness between accuracy for different applications, we often need to train a family of objectives with different queues. So for each different queue, one of the most important hyperparameters we need to tune is the learning rate. And so we might need to tune lots of learning rates for different queues. And second, federated networks are heterogeneous with extremely expensive communication. So our methods should be compatible with this constraint as well. So the high level idea is that our methods rely on some estimates of the step sizes corresponding to some specific queue. So we can dynamically estimate the learning rates based on the Lipschitzness of the objective. And also the method allows for low device participation and local updating, which have been also commonly used for almost every federated optimization methods. So I'll pause here if there are any questions. Okay, then I'll go on. So more generally, if we think about this empirical risk minimization framework, it has some nice statistical properties. So in this objective, it's a more general form, and N is the number of training points, and F is the loss function, and Xi is some training data. And it's a standard approach. Machine learning has nice properties, but it may be perform poorly when the empirical average performance is not an appropriate measure. For example, in the presence of noisy, corrupted, or imbalanced data, or if we want to encourage fair treatment of subpopulations, or if we want to handle distribution shifts between training and testing data. So this QFFL objective also gets us to think about a reformulation with the same intuition, but a much more general objective called tilted empirical risk minimization. So instead of minimizing the mean of the losses, tilted ERM term is minimizing this exponentially tilted average of the losses. So here T is a real valued hyperparameter that controls the impact of individual losses. We see that when T is positive, large losses will be upweighted exponentially. Let's see if I can get this. Okay. When T is positive, large losses will be upweighted exponentially based on the loss values. And when T is negative, small losses will be upweighted. Term in this way highlights outliers to promote fairness and suppresses outliers to promote robustness with this held hyperparameter T. So since there is a message in the chat, let's see if is this a question? Oh, sorry, no. Okay. So yeah, this is a generalization of this QFFL objective. And the takeaway for fairness is that vanilla ERM may deliver poor qualitative service to heterogeneous networks. And QFFL term allow for flexible trade-offs between fairness and accuracy. Are there any questions so far? Okay.
I think two questions coming up.
Yeah, I can see the chat. So at the beginning of the definition of federated learning, how to confirm the parameter PI. Also, PI is not learned parameters. It's usually some predefined constants that people usually set, like to impose weights to different devices. Like two typical ways are either we can set PI to simply be uniformly distributed, so 1 over the number of total devices, or we can set P sub I to be the fraction of the data points associated with that device. given, the server, I think we can assume that the server knows the number of training, roughly the number of training points on that device. And yeah, so if we think further about this, there are usually two ways, or at least two ways to do this optimization. Like one way is to to solve that objective with weights pi. Like there are possibly at least two ways. One is to first select the devices with weights proportional to pi, and then doing a simple average of the gradient updates or the model updates across the clients. And the second way is to uniformly sample the devices from the entire network, and then doing an aggregation based on this weight p sub I, which is usually proportional to the number of data points on that device. Yeah. So if we just directly solve that optimization objective, and I think if the aggregation happens at the server side, and the server needs to know the PI. So the second question is for the fairness in federated learning. The fairness may be violated by the distribution shift between training and testing distribution serial. So yeah, the shift between training and test distribution, I think, is a real concern in both in general machine learning and in federated learning. And I think there are, of course, many different notions of fairness in this setting. And in our work, we mostly consider a representation bias, which means that some subpopulation may not be represented enough during training, and that subpopulation can appear during the test phase. Hence, there is a distribution between training and testing data, and that can be addressed by robust optimization or this minimax fairness, or using our framework. And there may be different forms of distribution shifts between training and test data. For example, the P of the probability of the features may be different, but the optimal relations, like P of Y given X, can be the same across training and test distributions. And that's sort of more related to the setting where we consider domain adaptation in federated learning. And I feel like this is a generally less explored area in federated learning, and there are many different recent works to do that for general machine learning, but they're still very limited in terms of optimization, understanding the statistical properties of those invariant learning objectives, and so on. And so I think it will even be more challenging in federated learning to do this. Yeah. So I think this is a very interesting question in general. And from the fairness definition to this distribution, to exactly measure the form of distribution shifts, and also to think about how to scale the methods to massive federated settings. There are interesting research questions in all these aspects, I think. Yeah. So beyond fairness, there are various practical constraints in federated learning that are critical for deployment, including robustness, privacy, security, communication, and so on. And so those constraints are usually not coming in isolation. So previously, we only think about fairness, the trade-offs between fairness and accuracy. And here we look at the constraints between fairness and robustness. So here, fairness is defined again in terms of representation disparity, and robustness we look at robustness against data and model poisoning attacks, so training time poisoning attacks. And the constraints of fairness and robustness, they can directly compete with each other. So for example, to achieve fairness, previous methods usually outweigh those minority groups, and which may overfit to corrupted data. And to achieve robustness, methods tend to ignore those noisy samples, but this may filter out those informative information from the noisy samples. So fundamentally hard question in this setting is that it is difficult to define what is a corrupted data versus what is a good but underrepresented data. So fairness and robustness can be fundamentally at odds with each other. And also, and the previous issue can be, reformulated as the statistical heterogeneity problem. So that can be a root cause for the tension between these constraints. So our idea is to increase the model capacity by using personalization to achieve robustness and fairness jointly. So personalization methods usually learn separate but related models for each device, and they naturally model and adapt to the heterogeneity in federated learning. So instead of learning a single global model, personalization methods achieve an interpolation between learning global models and learning separate local models for each device. And there are potentially many ways to achieve this. And we use this simple and scalable multitask learning framework, DITO. And so DITO is inspired by the classic mean regularized multitask learning objective, but we regularize towards an optimal global model W star. So in this objective, we see that each device K solves a local objective over the personalized models VK, where we constrain VK to be close to W star. And W star is the optimal model by solving a global objective G, where G can be any aggregate function over F1 to Fk, so over the loss vector. For example, for this popular federated learning approach, Fed average, which is the objective we kept talking about before. And G is just a weighted average of these Fi's. So here I want to just give a little background of what fairness and robustness notions, again, we considered in this work. So the robustness we consider is Byzantine robustness, where the malicious devices can send corrupted model updates to the server. And in particular, we evaluate all three types of attacks. So label poisoning attack, random update attack, and model replacement. So those are commonly studied both in distributed and federated settings, which cover corruption at various points in the learning pipeline. And we measure robustness as the test performance across benign devices. So we don't consider, and we don't care about the performance on the corrupted devices. And in terms of fairness, we look at the performance uniformity across the network, which is the same notion as we talked about before. And the goal is to avoid bad performance for the underrepresented devices to encourage a more uniform performance distribution. And just to give some intuition of why DITO can be beneficial for fairness and robustness, and we first look at the DITO's properties in these simplified settings. So we have this federated point estimation problem where the local objective on each device K is to estimate the mean of these one-dimensional data points. So there are n data points on each local device, and we want to estimate the mean of those observed points. And so we consider this Bayesian framework. And suppose we have some random variable theta from some non-informative prior. And the underlying models on each device are generated by adding zero mean Gaussian noise with variance tau squared to theta. So from V1 to Vk, those are the real means on those devices. And tau is viewed as a task relatedness parameter. So if tau is 0, and the data on all devices will be coming from the same underlying distribution. As tau gets larger, then the devices will become more unrelated. And we assume that there are n local training samples that are observed on each device. And those observed training samples are obtained by adding this Gaussian perturbation to the underlying mean. And we also assume there are K sub A malicious devices, where each having the attack ability modeled by tau A, where tau A is larger than tau. So under that setup, we can explicitly characterize the closed form of an optimal lambda star. So recall that lambda star is the hyperparameter before the global regularized term, so that controls how much we do local training and how much we do global training for each device. And we can have this closed form solution of an optimal lambda star, which is a function of these important parameters. It's a function of number of local samples, task relatedness parameter, and number and the ability of malicious devices. So we see that the test accuracy and variance across devices will be jointly minimized with the same lambda star, which means that the solutions under this lambda star will be optimal in terms of both fairness and robustness. So a single lambda star will achieve the best of the both worlds. And when the number of local samples goes to infinity, we tend to train local models. And so when n is close to positive infinity, lambda star will be close to 0. And when k sub a is close to infinity, or tau a is close to infinity, which means that the attack ability is infinite, we also tend to train local models. And because in that way, and in that case, the global model will be infinitely corrupted, and there's no way to do this federation. And when there's no corruption, as tasks become more different, so when tau increases, we tend to go from global training to local training. And when the data is RID, independent and identically distributed across the network, which means that tau is 0. Personalization only helps when there are attacks. So when tau A is larger than 0, and lambda star will be smaller than some positive infinity. Otherwise, when tau is 0, which means data are identically distributed and there are no statistical heterogeneity. And when tau A is also a 0, which means all the data are clean, the optimal choice is to go with the global training option, which means that the optimal lambda star is positive infinity. And so those are the results we get, and here are some of the figures visualizing those. So in either clean or corrupted case, data with lambda star is better than both local training and global training. And as devices become more related, we tend to go to global training with a higher lambda star. And the error bars of three methods are showing the empirical variance of test errors across all devices. So DITO has a lower variance of test error, which means that it's more fair. And in adversarial cases, DITO has lower test error on benign devices, which means that it's more robust. Yeah, so the intuition, we only prove that in linear cases, but that should, the relations of those parameters should generally hold in general problems. And how to solve DITO? So we can alternate between solving for the global model W star and personalized models, PK. So the updating of the global model does not depend on personalized models. And in that way, DITO can be viewed as a lightweight personalization add-on to any existing global solver. So in that sense, it's scalable in federated learning for both convex and non-convex problems. And also the information transmitted between the local devices and the server is exactly the same as if you were solving for a global model. And DIDO preserves the practical properties of the existing global federated learning methods with convergence guarantees. So a key advantage of DIDO is its modularity, and this has several benefits. So in terms of optimization, we can plug in any global model solver and inherit the convergence benefits. So formally, if the global model W star converges with rate GT, and then so T is the number of iterations, and then we prove that there exists a constant C, a bounded constant, such that DIDO converges with rate C times GT. So DIDO's convergence can be improved by using any recently developed methods with a better global convergence rate. And also, DIDO enjoys exactly the same privacy and communication benefits of the global objective and its solver. And further, we can plug in existing robust methods, such as those robust aggregators, to robustify W star, which can further improve the performance. So are there any questions so far? Okay, so empirically, we show that fair methods can be more sensitive to attacks because though they can easily overfit to corrupted devices. And robust methods, for example, those robust aggregators such as multi-crom, they can filter out rare but informative updates from benign but underrepresented devices, resulting in unfairness. And DIDO is both fair and robust on this attack. And we also compare DIDO with state-of-the-art robust or fair baselines. So under the various attacks we described before, for all levels of corruption, DIDO outperforms the strong baselines, including the medium aggregator, gradient clipping, and crom. So those are some popular classic methods that people proposed before. And if we look at the performance variance, and DIDO is also more fair than the fair methods. So on average, it improves the absolute test accuracy by around 6% over the strongest robust baseline. And in the clean cases, it reduces variance by about 10% over state-of-the-art fair objective. So are there any questions? Okay, so lastly, I'd like to briefly mention some of the future works. And in terms of personalization, there are many ways people can do to personalize models, which is to allow the information sharing between the devices while also learning separate but related models for each device or each organization. And it's not yet clear what is the optimal for personalization formulation for federated learning. And another question is the differences between federated meta-learning and classic meta-learning settings in terms of how to evaluate and how should we think about the relations between different tasks. And further understanding on the benefits of personalization for other constraints such as privacy, and for other notions of fairness and robustness, and also the privacy implications of personalization. And in terms of fairness, it will be interesting to explore the interplays between fairness, privacy, and robustness, and rigorously show how fairness benefits how multitask learning can benefit fairness. So in the Statistical example, we only theoretically analyze that in that simple linear case, and it will be interesting to explore it for the more general case and for possibly different definitions of fairness. And also the connections to the notions of algorithmic fairness and how should we think about algorithmic fairness, including group fairness and individual fairness in this setting, and other definitions, solvers, scalable solvers, or optimization methods for federated learning. And in terms of diagnostics, one fundamental question is that it's not clear how to determine the heterogeneity or the device relatedness a priori before training, right? And can we have some lightweight and effective methods for that? And if we have that diagnostics of heterogeneity, what is a good way to leverage that for improved performance of the downstream tasks? And also there are other open questions, including those related to benchmarks and privacy, security, and semi or unsupervised federated learning, and so on. Yeah, thanks. That's all I have today. And the references and all the papers mentioned before are all available online, and all the code are open source on GitHub. And I'm happy to take questions if there are any.
I think there is a question in the chat box.
Oh. From the objective detail, an intuition explanation about why it benefits fairness and robustness. Okay, so the detail objective is a simple multitask learning objective where it jointly training, it's just can be viewed as some sort of fine-tuning on the local devices after we have learned a optimal global model W star. So in terms of robustness, it's a little bit more clear than the fairness benefits, because we're using some of the local data to improve the performance of personalization. Okay, so if we only training a single global model, and it's very unlikely that the model will work well for all the devices. But if we use DIDO, and then if some device is a benign device and its data are all clean, and then further fine-tuning on these clean data should be beneficial for robustness. And for fairness, I guess, so in our experiments, we observed that the devices with a lower accuracy by using a single global model will be improved and will have a improved performance with an higher than the performance improvement on the worst performing devices will be higher than the performance improvement on the devices which already have a good performance. So in that sense, detail will benefit fairness. So if we want to think about it more rigorously, and we can use that an analytical framework I described before, which is to see how detail can benefit the variance using an optimal lambda star. Yeah. So we're measuring the fairness in terms of the performance variance across all the devices, and that variance will be minimized for under this specific lambda star. Yeah. And any comments on bias issues? Yeah, so I guess that's a good point. The bias is a very general term, and in federated learning, it can mean many things. And so representation bias is one that we discuss the most today, which means that some of the population or or a subset of the devices will not have enough exposure during training for different constraints. For example, those devices may have a very slow network connection, or its computation power is not strong enough for it to finish the training in a given time window. So that part of the devices will be disproportionately disadvantaged in the training. And we want to produce some models that will work well for all devices, basically, for all combinations of the training distribution, like during task time. So I think both in the general machine learning area and in federated learning, this has been studied. And there are some unique challenges associated with federated learning. Like first, the use cases in federated learning may be very different from what people see in centralized environments. For example, in federated settings, there may be some temporal distribution shifts, like the training data distribution will be very different during the daytime and the nighttime. And this might also cause some form of bias. And also in terms of optimization, the challenges of distributing things in such massive networks always exist. Yeah, so I think it's generally an open area, and there are lots of potential interesting directions there. And compared with federated multitask learning, is Ditto more scalable? I think so, yeah. So by federated multitask learning, do you mean that Oka paper? Yeah, I think Ditto is more scalable than that, because we are it's just like interpolating between local and global models, and we are not using some relationship matrix to constrain that, and all our convergence guarantees and everything, and most of the analysis will hold for both non-convex and convex problems. So Ditto can be viewed as multitask learning with just two tasks. The one is the global task and the other is the local task. And so we're alternating between solving for the global task and solving for the local task. So it's more, one of the properties of Ditto is that it's more scalable than this federated multitask learning formulation. Yeah, I think so. So although federated learning models keeping the data locally, privacy in data could still be leakaged, may it affect the application of learning? Oh yeah, so we haven't touched privacy today, and privacy is definitely a very important question in federated learning. And so there are different ways to protect privacy. Like we can either go with the differential privacy direction, or go with the crypto-based methods, or combine these two. Since it seems that the crypto-based methods do not scale well in large-scale settings, so people most of the time will prefer to use differential privacy, because it gives us a nice and rigorous mathematical formulations to both optimize for and measure privacy in machine learning training, including federated learning. But I guess the first basic question we want to think about is how to define privacy in federated learning. So differential privacy, it's still open, like if differential privacy is the appropriate metric for privacy. There may be some other matrices depending on the real life applications. And in the scope of differential privacy, there are also some other issues like how to make it work better when the model dimensions are high, or how to make it compatible with other constraints like fairness and robustness and communication. And so, yeah, so I think it's also an interesting open area. Yeah, thanks for the questions.
Great. Thank you for your quick question and a very, really nice talk. I think your talk is really, really interesting. Many audience are asking many intriguing questions. Thank you again for your talk here. In the near future, when the situation is lifted, hopefully you could physically visit us in Tokyo, in our Nihonbashi office. Thank you again. It's a great talk.
Thanks, everyone. That's nice discussions.
Great. So, okay, right. Next, let's welcome our second guest, Nina Marabi, to give her talk. Hi, Nina. Can you share your screen right now?
Yeah. Hello. Yeah, sure.
Great. Hi, Nina Marabi received her bachelor degree in computer science and engineers from University of Southern California. She is currently a PhD candidate at the University of Southern California Information Science Institute. Her research is on developing trustworthy AI systems with an emphasis on algorithmic fairness in machine learning and natural language processing. She is a part of MINDS group advised by Aram Goldstein and a recipient of 2021 and 2022 Amazon Fellowship from USC Amazon Center on Secure and Trusted Machine Learning. Let's hugely welcome Nina to give her talk, Unveiling Bias in ARP System. Hey, Nina, please proceed.
Hello. Yeah. Hello, everyone. Thank you so much for inviting me and also your participation. My name is Nina Marabi, and today I'm going to be talking about some of the work that we have done in identifying different types of biases in NLP systems and some methods to mitigate effects of biases or unfairness in our systems. I also want to thank my collaborators who helped me in these three works that I'm going to present in this talk. So as you know, machine learning and natural language processing systems are being widely used in our everyday lives and even in some high-stakes decision-making processes. So it's really important to understand existing biases and harms in our systems. And this is important so that we have methods to mitigate such harms. So in this presentation, I will talk about some of the biases that we observed in some applications. And lastly, I'm going to talk about methods to mitigate such effects. So during this presentation, I'm going to first talk about biases that we observed in common sense reasoning tasks and resources. Then I'm going to focus on another application in NLP, namely name entity recognition systems. And I'm going to talk about another types of biases that we observed in these systems. And lastly, I'm going to talk about how can we have more interpretable fairness imposing algorithms, and whether or not we can use interpretability frameworks to achieve fairness in our systems. So I'm going to start with our first work, biases in common sense reasoning tasks and resources. And I'm going to introduce some biases in knowledge bases and downstream tasks that are utilizing these knowledge bases. So to start off, I'm going to explain what common sense knowledge is. Common sense knowledge is facts about the world that all humans are expected to know about. So based on this definition, we expect common sense knowledge to just be facts and not be any stereotypes or biases in terms of favoritism or prejudice against any individual or a group. So if we have a knowledge base, we expect this knowledge base to contain only facts and not stereotypes or associations to certain groups. So for instance, these are types of concepts that we accept to be available in our knowledge bases. So fish is capable of swimming is an acceptable concept because this is a fact that we expect humans to know about, and it doesn't contain any biases or stereotypes against any group. Or a fish is located in water. However, there are some undesirable cases in our knowledge bases that we observed that is not necessarily correct to appear in our knowledge bases, because it's gonna later form our models to have these stereotypical or biased associations towards some individuals or groups. So the first example is politician is capable of telling lies. So you might ask me, okay, why are you saying this is not an acceptable fact? Politician is a human and all humans are capable of telling lies. It is true, but this is not true when we only associate liars to politicians. Meaning if we have tons of occupations and we are just associating politicians to be liars and doctors to be trustworthy people, there is also a negative associations or stereotypes that we are assigning to certain demographic groups. So we want to be more identical across groups if we have such stereotypical views. Or in the case of second example, it's an extreme case which we do not expect to appear in our knowledge graph. So this is not acceptable. It's a pure bias against church. So in this study, we wanted to quantify harms in common sense knowledge resources and observe such cases. I think there's a question, right? Sorry. Oh, okay. So in this study, we studied two knowledge bases, namely ConceptNet and Generics KB, which are widely used in NLP systems. And then we studied two downstream tasks that are utilizing these knowledge bases, more specifically ConceptNet, namely common sense knowledge generation or completion and common sense story generation. And then we proposed a mitigation framework based on a pre-processing technique that is using a filtering idea. So before explaining this work in more detail, I'm gonna talk about different types of harms or biases that we see in our machine learning and NLP systems. On one hand, we have allocation harms, and these are harms when a system withholds certain groups some resources or opportunities. So for instance, if you have a loan allocation system and this system is assigning loans to certain demographic groups while it's withholding loans from another demographic group with similar characteristics, then we call this system to suffer from allocation harm because it's obviously withholding some opportunities or resources from one group while not for another one. A characteristic of allocation harm is that it is really easy to quantify. You see nowadays there are tons of papers in fairness that they come up with some fancy fairness definitions or metrics that are trying to quantify allocation harm. For instance, if you take the simplest metric, statistical parity, what it does is it tries to equalize the probability of getting the positive outcome among different demographic groups, which is exactly tries to minimize the effect of allocation harm, because the positive outcome in this case is assigning resources or opportunities to these groups. On the other hand, we have representational harms, and these are harms to the identity of certain groups to make them appear inferior, regardless of allocating them resources or opportunities. So in the example that I just described, to associate politicians to be liars, this is an example of a representational harm. Why? Because we are representing politicians in a way that we are making them to appear inferior. So we are not necessarily withholding any resources or opportunities from this demographic group, politician in this case, but we are representing this group in a way that is not proper. So a characteristic of representational harm is that it is difficult to formalize. And depending on what application your focus is, you might change your definition of representational harm. For instance, in image, you are representing some groups by labeling them inappropriately. So there you might have another formalization for representational harm. And in text, you might have another formalization. So the focus of this talk is gonna be in representational harm specifically. So then our definition of bias or harm becomes the existence of prejudice or favoritism toward an individual or a group based on their identity. In this work, we proposed 3 different types of representational harm, namely overgeneralization, disparity in overgeneralization, and disparity in frequency. By overgeneralization, we mean if there exists prejudice or favoritism toward individuals or groups. And by disparity in overgeneralization, we mean how different individuals or groups are represented in terms of overgeneralization harm. So notice the difference. For overgeneralization, we are just focusing on one specific group, let's say American, and we want to see how are we representing American people? Are we always being nice to them? Are we disfavoring them? Or are we just having some facts to represent these groups? So for overgeneralization, we are just focusing on the group itself, and we want to see how are we representing this specific group. For disparity in overgeneralization, we look across groups, meaning if we have groups like American, British versus another nationality, if we are being in favor of Americans while against British and neutral about another group, then there is obviously a disparity. So we want to also observe these disparities that exist in our knowledge bases. And lastly, disparity in frequency, which means is the knowledge that is representing a group sufficient enough? Meaning if we have thousands of concepts to describe Americans versus only 2 for British, then obviously we might not be able to describe British people well. Notice not necessarily having a lot of knowledge is a good thing, because it might be the case that all these knowledges are just being in favor or prejudice and they do not contain any facts about this demographic group. So that's why we have this overgeneralization concept as well as disparity in overgeneralization with disparity in frequency. So ideally, we want a knowledge base that first has sufficient knowledge in representing groups, and second, it's representing the groups in a factual manner. So that's the overgeneralization part, and then we have the disparity in frequency. So then the question becomes, how do we quantify these types of harms? So knowledge is represented in form of triples in most of knowledge bases, including ConceptNet. So what we do is we first convert triples to natural language sentences. So here you can see an example of a triple. American, comma, is a comma, citizen of America. What we do is we convert this triple to a natural language sentence. And in ConceptNet, these relations are predefined. So we just use a simple templated mapping to map triples to sentences. However, this is an active area of research on how to convert triples to sentence itself. But here we are just simplifying it by mapping the relations to its natural form. After having this sentence, we apply sentiment and regard classifiers and obtain sentiment and regard labels. So you are already familiar with sentiment classifier. If it happens that sentiment is assigning a positive label to this sentence, we might say that we are favoring this sentence according to sentiment classifier. If sentiment is assigning negative label, we might say we are being prejudiced, and neutral is our ideal case. So notice we are using sentiment and regard as proxies to biases. Regard is similar to sentiment, however, it's specifically trained to capture biases against different demographic groups. So again, if we have a positive label, we say that we are favoring this group according to regard, neutral is the ideal case, and negative is the prejudice case. Previous work has shown that sentiment and regard classifiers can themselves be biased. So what we do is we mask demographic groups when we are using these classifiers and only focus on the concept that is described in the group to avoid biases from sentiment and regard to seep into our analysis. Okay, then the question becomes, how do we formalize these 3 terms? So for overgeneralization, we report the percentage of positive, negative, regard or sentiment labels over all the sentences for that target group. So for instance, if you are analyzing Americans, if we have 10 concepts representing Americans, out of those 10, 5 are associated with negative sentiment label, we say that the negative overgeneralization with regards to sentiment is 50% for American group. So we do the same thing for positive, negative regard labels, and we report overgeneralization as the percentage. Disparity in overgeneralization, we use variance in positive, negative overgeneralization scores that we obtained for different target groups. And disparity in frequency, similarly, we use variance in frequency numbers for, again, different targets that we are studying. So we studied more than 300 target groups from 4 different categories, namely origin, profession, gender, and religion. From the origin category, we have target groups such as American British representing their nationality, profession, some occupations such as nurse, psychologist, etc., gender, man, woman, religion, Muslim, Christian. So in this talk, when I talk about categories, I mean these high-level categories, origin, profession, gender, and religion, and target words are the instances for each category. So the first question is whether sentiment and regard are good proxies for biases. So what we did was we took 3,000 instances from ConceptNet and more than 1,500 from Generics KB and asked human labelers on Amazon Mechanical Turk to label these triples to be either favoritism, prejudice, or neutral facts. So we wanted to compare how humans are perceiving bias versus sentiment and regard. And we found out that sentiment and regard are in a reliable agreement with human labels. Moreover, we compared sentiment and regard labels to a simple keyword-based approach, meaning we have 2 dictionaries, one on words that might describe a favoritism situation and another for disfavoring situations. And if a sentence contains some of these words in the dictionary, we label that sentence to be either in favor or disfavoring or neutral facts. And we figured out that sentiment and regard are outperforming this simple approach. And because they're in high agreement with humans, we conclude that sentiment and regard can be good proxies to capture biases. So from our results, we show that both ConceptNet and Generics KB have the overgeneralization and disparity in overgeneralization issues. And the degree of severity is higher in Generics KB compared to ConceptNet. So in the plots, you can see there are some outliers that spread. So this shows there are some target groups that we are overgeneralizing them. And you can see the spread of boxes on how the disparity in overgeneralization is. And if you notice for Generics KB, there are some outliers that go up to 100% for regard classifier and up to 80% for sentiment, while for ConceptNet, the most severe case is up to 30%. So this already shows us that Generics KB has more biases against some of these target groups compared to ConceptNet. And in the plot on top, you can see some qualitative examples from the profession group. And you can see this according to regard classifier. There are some occupations such as CEO that are in the favoritism region, meaning we are perceiving these groups as positively. And some occupations such as politicians or performing artists are in the prejudice region. We ideally want all the target groups to lie in the green region, which is the negligible bias region, similar to where mathematician and hairdresser are. But unfortunately, you can see the spread and how differently we are representing different occupational groups in our knowledge bases. So here are some results from the frequency analysis, again on both ConceptNet and Generics KB. You can see again the existence of outliers and the spread of boxes and some qualitative examples. So for British group, we have lots of knowledge, but not so much for Saudi Arabian. And again, having a lot of knowledge is not necessarily a good thing. That's why we have to do the overgeneralization analysis as well. And again, you can see for the religion category, Bible versus Quran, or in generics KB, scientist versus hairdresser, or woman versus man. So again, we see the issue of disparity in frequency in these knowledge bases as well. So that was all about analyzing the knowledge bases itself. Now we look into downstream tasks that are utilizing these knowledge bases, namely COMET and Common Sense Story Generation that use ConceptNet. So COMET is a knowledge completion generation model. It is trained on GPT and then ConceptNet. We input the same target words that we used in analyzing ConceptNet as prompt, and we collect triples by following all the relations that exist in COMET. And we obtained around 112 case statements that we analyzed the bias the same way we did for ConceptNet. And in Common Sense Story Generation, given a prompt, the model will generate 3 to 5 sentences to tell a story. It extends GPT-2, then post-trained on Common Sense knowledge from Atomic and ConceptNet, and further post-trained on Drug Stories corpus. So we created 30 templates, and we populated the templates with the target groups that we were studying. So we observed 3K prompts. And again, each story is 3 to 5 sentences. So we obtained 12K sentences to apply the analysis over. I think there was a question, if I can.
Yes, there is a question in chat box.
So, so the use of sentiment and regard makes us able to do this automatically. So sentiment and regard are just classifiers that can flag if we are using it as a proxy for bias. So if they flag something is positive or negative, then it's automatic. We are not doing any intervention then there. But that is only for analyzing the knowledge base itself. So now that I'm gonna explain the downstream tasks, which are actually learning models, I think things are gonna be more clear on how they affect the downstream tasks, which are actually learning models. So everything I talked about was on the knowledge base itself, but from now on, it's gonna be the downstream tasks that are using these knowledge bases, if it answers your question. So yeah, so these are the tasks that are using ConceptNet and are trained on ConceptNet. And again, we see another question. Okay. We see that again, bias exists both in COMET and Common Sense Story Generation. You can see the outliers that are showing the overgeneralization issue and the disparity in overgeneralization. And some interesting thing to notice is that if you remember, the most severe case for ConceptNet was 30%, but in analyzing COMET and Common Sense Story Generation, outliers go up to 50% or 60%. This shows us that not only bias is propagated to these downstream tasks, but the bias is even amplified. So we have this issue of if a model is trained on a biased data, in this case, knowledge base can be considered as your data set. The bias can even get amplified in some cases, which we see here. So then we propose a bias mitigation framework that is using a data filtering idea. So what we do is we take the knowledge coming from the knowledge base, in this case, ConceptNet, we apply regard and sentiment classifier, and we filter out the knowledge that is not facts according to these classifiers, or they are problematic. Now we have this filtered knowledge base or data set. Now we train our downstream model COMET on this filtered data set. And we hope that by this pre-processing method, we are gonna mitigate the biases that exist in our systems. So then we compared Comet with this filtering approach, Comet filtered, and asked human labelers to label 3,000 triples as being biased or not, and if the triple makes sense, so if it's a valid triple or not. We observed from our results that Comet filter is reducing the bias compared to Comet, but we are having lower quality compared to Comet. So this shows we have a trade-off between fairness and quality, or in this case, we are observing that the triples are not as valid as what Comet would generate. So an interesting future direction can be, how can we train models that are fair, but at the same time maintain the high quality that the original models have? So we see this fairness accuracy trade-off in many applications, and we see the same thing happening in our case as well. So here are some possible future directions. So can we have better proxies for bias than sentiment and regard? Can we have better mitigation strategies that can reduce the bias even more at the same time and maintain the original quality? And can we separate the bias that is coming from the resources, such as common sense knowledge bases, from the biases that are injected in the downstream tasks while we are training them? So these are some interesting questions that, if you're interested in this type of work, you can think about. So that was all about the first work, analyzing biases in common sense reasoning tasks. I'm gonna move to our other work, that is analyzing biases in name entity recognition systems, which is another NLP application. So in this work, we were interested in investigating existing gender disparities induced by name entity recognition systems. So in NER, given a text, NER model will label entities and their types. For instance, if you have a sentence, Nina is going to school, Nina should be identified as an entity and the type should be labeled as person. So we wanted to see, is it possible that male names are recognized and tagged more correctly compared to female names, or vice versa? Or what would be the best cause if this is happening, if this type of biases exist? And how can we evaluate these systems? What metrics can we propose? And can we somehow quantify these disparities? So we found out that yes, indeed, name entity recognition systems do not perform equivalently across names from different genders, and more female names are being mistagged or not tagged at all compared to male names. So here are some examples in the figure. You can see Charlotte is a person. Charlotte is correctly identified as an entity, but its entity type is mistagged as being city. Or Isabel is sleeping. Isabel is correctly identified as an entity, but its tag is wrong. It's tagged as miscellaneous. Or in some more severe cases, Rose plays with her dolls or Olivia drinks water. Rose and Olivia are not even recognized as an entity. So we wanted to evaluate NER systems by creating some templated sentences such that they can force the NER model, if they are doing the right job, to tag the entity as a person entity. So in the table, you can see the templated sentences that we created. Some of them are more neutral sentences, such as is a person, that we expect both genders to have equal outcome if the NER system is doing the right job. But some of them can capture more of societal biases. So for instance, someone is going to grocery shop. Historically, it's more believed that female are gonna go to grocery shop. So it might be the case that more female names are being tagged in this scenario versus male. Or is a nurse versus is a doctor. Maybe it's the case that more female names are gonna get recognized in the first case versus the second one. So we both analyzed the cases where the template is neutral and also investigate other cases as well. Then we started to quantify biases in NER systems by proposing 6 different metrics. So in error type 1 unweighted, we are interested in seeing whether the entity is not tagged at all and or its tagged is other than a person entity. So if this is the case, we call it an error. And for error type 1 weighted, which is similar to unweighted case, we consider the frequency of the name into consideration. So we analyze census data. If a name is more frequent, meaning popular, then we want to punish our system more if it misses such popular names. So this is the difference between unweighted and weighted cases. In error type 2 unweighted, we are only interested in cases where the tag is mistagged. So we don't care if something is missed. All of the ones that are tagged, which ones are mistagged. And again, we have error type 2 weighted, which considers the frequency. In error type 3, we are only interested in the cases that we are missing to identify them as an entity. And again, we have the similar case for the weighted, except we consider the frequency. So notice here, error type 1 is a superset of type 2 and 3. So you might say, why do we even need type 2 and 3? It's the case that we want to know if something is missed, or if we consider something as an error, is it the case that we didn't recognize this as an entity, or the tag that we are assigning is wrong? So we wanted to do this more fine-grained analysis. That's why we have error type 1, which is the superset, and type 2 and 3. Then we analyzed 5 different name entity recognition systems over names coming from 1875 all the way to 2015. And we found out that in all these name entity recognition systems throughout history, according to these different error types, female names have higher error rates than male names. This is a problem, right? Because it's so consistent for all the name entity recognition systems throughout history. For all the error types, female names have higher error rates. So this is a problem. And also you can see some qualitative examples in the tables. Charlotte is a very frequent name, but it's mostly mistagged as location, or similarly Sophia from female group, or Victoria. And you can see some other examples for the male names, such as Christian, Jordan, etc. So then we want to know what is the reason. So we analyzed 2 widely known data sets that these NER systems are trained on, namely Connell and OnToNodes. And we figured out that in census data, which is representing the reality, female names have more variety compared to male names. But in our data sets, we don't see that variety. And it's exactly the opposite. Male names are more versatile than female names. So obviously, we are not able to cover female names as they are in the reality, because the data sets are not properly representing these female names. And moreover, these data sets are news-based data sets. And news already is biased contextually against female. So for instance, if you have a sentence, President Bill Clinton is visiting Sophia, Sophia is more likely to be a location in this context, whereas Bill is a person entity. So news already has this contextualized bias as well against women, which is amplifying the bias. So not only we have this coverage issue, but the context issue as well. So some, again, possible future directions for this work is, can we design NER systems that can reduce the gender disparities introduced in this work? Can we use contextualized knowledge to help these cases? Because if the model is recognizing the context, it's easier for the name to be tagged as the correct tag it should be. And can we make data sets that are more versatile and representative by some data augmentation techniques to improve our NER systems? So these are some questions that we can ask. Some questions. Yes, this is a good question. So indeed, if the data was more representative, we could at least alleviate some of the cases that we were seeing in our data sets, because the data set is obviously not having coverage. But as I said, there is this context issue as well. In the news context, because news is biased already, we have this issue of mistagging. So having data augmentation might help us in a sense that we are tagging more and more female names, but we also have this issue of assigning the correct tag, which we should use some contextualized knowledge on top of the simple data augmentation. So I think both of these are important, both coverage and also how we represent these groups. If this answers your question. So that was all about analyzing biases in NER systems. Now I'm going to actually, you might say, okay, she's only talking about analyzing biases. What are ways to mitigate biases or unfairness? So here I'm going to talk about a work that can, another question. So as far as I know, we are one of the first who came up with this. So we are just using this simple templated format, but there are other works that are trying to see how robust NER systems are. They are not specifically on fairness, but more robustness of NER systems. But in terms of having so many works in this area, that's not the case. And indeed, that's why we are encouraging people to work on how can we address this issue, because it's not an easy problem to solve. There is this tons of data sets that we either need to augment or better models. Yeah, so that's what I was trying to say exactly, because in news there is this contextualized bias. So again, female names can be represented in a way that they're not assigned the female tag correct, like the person tag correctly. So that's why it's only not a data issue. We need to also study data sets to see if there is contextualized bias in them as well or not. And indeed, in our results, we found that the methods that are contextualized, using contextualized embeddings, they are more powerful than non-contextualized ones because they are using the context to infer the name. So this is something to consider. It's not just data, but how are we representing entities in our data set as well according to context. Yes, again, but we need to be careful of if GAN is generating the context correctly. Again, there is this issue of representativeness or so if you remember, we had these 3 types of errors. Is it that we are missing it? GAN might help perhaps in the missing part, but we might also be careful about error type 2 that we describe, as in the tag should be correct. So GAN should generate something similar to our templates that is forcing the model to label the entity as person entity. So perhaps having these templates is really naive, so you might need to do more sophisticated cases there. Okay, so now we are going to on how to reduce unfairness or bias in our systems. We talked about biases or how to analyze biases, but how can we actually mitigate this effect? And not only mitigation, but how can we be interpretable while we are mitigating? So we just don't want a black box model that is mitigating unfairness. We want to know exactly what is causing the unfairness and how can we mitigate unfairness in an interpretable fashion. So by now you should be well motivated on why we need fairness as well as interpretability, because again, machine learning models are being used in sensitive environments such as healthcare or parole decision systems. So it's important for our models to be both fair as well as interpretable. So interpretability is a desired feature of ML models. Why? Because we need to know how a model generates a certain outcome. And we also want an interpretable way to achieve fairness. We want to know exactly what features are causing the model to be biased and how can we mitigate this effect in an interpretable fashion. Why is this important? Because the decisions need to be audited, understood, and defended, especially in these high-stakes environments. So to have an interpretable neural model, we propose to use a classification model with attention mechanism. And then we propose this attribution framework that intervenes on the attention weights to reason about the importance of each feature on the outcome. And here, by outcome, I mean fairness of the outcome. Then to achieve fairness in classification, we utilize the attribution framework and design a post-processing bias mitigation strategy by diminishing the effects of the problematic features that were detected by the attribution framework to be problematic. So here is the outline of our approach. First, I'm going to talk about our general classification model that utilizes the attention weights. Then I'm going to talk about attribution framework that tries to reason about the effect of each feature on the fairness of the outcome. And lastly, our bias mitigation strategy that is using the attribution framework to mitigate bias in an interpretable way. So here is our classification model, which is similar to how text classification is done in NLP, except we extend it to tabular data. So we consider each feature as words are in sentences, and we learn an embedding for each feature. Then we pass these embeddings to the attention layer. We get an overall representation for this instance. We pass it to the dense layers, and we get our outcome for the classification. So this is the general model that many of you may already be familiar with on how text classification is already done using attention. Then we have this attribution framework that tries to reason about the effect of the Kate feature, in this case, specifically fairness. Previous work has tried to analyze if attention is interpretable or not, and they used a similar framework for analyzing the accuracy. Here, what we do is we calculate fairness differences, meaning we calculate the outcome first. We calculate the statistical parity or any group fairness metric first, and we compare to the secondary outcome. And then this difference between statistical parity measures is gonna tell us the effect of the Kate feature on the outcome. So here is how we do this. So we get the output of the classifier with all the attention weights intact, meaning we learn our classifier, we learn our attention weights, we don't touch the attention weight, just get an outcome for the features as they are, and we call this outcome out. Then we zero out the attention weight corresponding to the Kate feature and obtain a secondary outcome out prime. Then to know the effect of the Kate feature on outcome, we observe the differences by calculating difference in fairness metrics of the original out and out prime. So again, here notice you can use any fairness metric, any group fairness metric, as long as you can measure it before and after removing the effect of the Kate feature. So this is how we reason about the effect of the Kate feature on the outcome. If we notice that by removing the Kate feature, we are achieving higher fairness, we know that this feature was problematic, because if we are removing it, our outcomes are more fair. So then we use that attribution framework and design a post-processing bias mitigation algorithm as such. So first we use the original attention model and obtain all the attention weights for all the Kate features in all the eye samples. So this is similar to saying we use the attention-based classifier and obtain attention weights. Then we observe the effect of the Kate feature on fairness by zeroing out its attention weight. Again, this is similar to using our attribution framework and reason about the effect of the Kate feature on the outcome. If the feature contributes to unfairness, we add it to the unfair feature set. And we do this for all the Kate features that exist in our data set, and we either mark them to be problematic or not. For all the features that are flagged as problematic, we use a decay rate value to decrease the effect or attention weight of that feature on the overall attention weights. So now we have newly obtained attention weights that we hope is going to be more fair because we have reduced the effect of the problematic features in our algorithm. So in our experiments, we wanted to verify two things. First, if our attribution framework is correctly identifying the problematic features. So if this is the case, we expect that using higher or severe decay rate values is gonna increase fairness for us. Second, we wanted to see how are we being comparable against the state of the art that are trying to be more fair. So for this, we analyzed tabular data sets, namely UCI adult and heritage health data sets. And we noticed that, yes, indeed, the attribution framework is correctly identifying the problematic features. Why? Because by decreasing the effect of the problematic features, you can see a decrease in unfairness. In this case, we are analyzing statistical parity difference, but you can check our paper for all the other metrics as well. Moreover, we are more or less comparable to the state of the art. So for UCI data set, we are the best. And for heritage health, we are second to the best. One thing to notice is that there are some flaws that these state-of-the-art methods are not interpretable. So they're just black box models that are trying to mitigate unfairness. While for our case, we know exactly what feature and by how much it was manipulated to get this outcome. And secondly, some of these state-of-the-art methods, such as FCRL, which is one of the best in this case, is only applicable on statistical parity measure. So it wouldn't work on any other fairness metric. I'm gonna later explain what other advantages our model has over state-of-the-art. We also did some analysis on non-tabular data, in this case, text data. So we use the bios data set. This data set contains bios of individual, and then the prediction task is the occupation of the bio. Previous work has shown that this task can be biased because if there exists some gendered words in the bio, it's more likely for the model to label the bio to certain occupations. So for instance, if you have female-related words in your bio, it's more likely for the model to predict nurse, while in reality, the occupation might be dentist or doctor. So we analyzed the differences between dentist and nurse and compared the non-debiased model, which is naively just training on the data set, versus a pre-processing baseline that is masking the gendered words before training, and compare it to our post-processing method that I described in this work. So we show that our method is able to mitigate bias the most, but the non-debiased method is the most accurate method. However, you can see that our method is having higher accuracy compared to the pre-processing. So we both decrease the bias and at the same time maintain higher accuracy than the pre-processing baseline. And you can see here some qualitative results as well from some of the bios. You can see that the green regions are showing where the model is putting the attention weight to have the prediction. And you can see for predicting the job nurse, our method is putting the attention on words such as RN, short for registered nurse, which is an informative word, while the pre-processing method is not capturing that meaningful of a word to predict. And more interestingly, you can see that the non-debiased model is only focusing on gender-related words such as she or Rebecca, which is a female name. And this is exactly where the bias is coming from, which is undesirable. So I wanna highlight some of the advantages that our method has over state-of-the-art. First, we are able to provide explanations such that the user exactly knows what feature and by how much it was manipulated to get the corresponding outcome. Second, adjustments to attention weights in our model is done post-training. So we only need one round of training, which can be really efficient in production setting. In production setting, you have a large data set. It might be expensive for the models to be retrained for different sensitive attributes, for different fairness metrics. But for our case, that's not the case. We just train once and all the mitigation is done after training. So you might one day come and say, my sensitive attribute is race. I want to be race according to fair according to race. You train one model and next day you want to be fair to gender. So you need to train another model. But this is not the case for our method. For our case, it's also possible to achieve different trade-offs by controlling the decay rate value, and not only fairness, but you can have trade-offs between accuracy and fairness. So you can also reason about accuracy as well, and don't touch the features that are helping accuracy, only the ones that are hurting both accuracy and fairness. Our approach doesn't need to know the sensitive attributes while training. Again, because everything is done post-training, so it could work with any sensitive attribute, any hyperparameter setting, any fairness metric, as long as you can measure before and after changes. And it's also scalable for large-scale data sets because it's a neural model, as well as textual data that we discussed in our analysis. So to conclude in this talk, we investigated some biases that can exist in some NLP applications, namely common sense reasoning, resources and tasks, and name entity recognition systems. We investigated potential causes and some suggestions for their mitigation. And we lastly talked about how interpretability can help mitigate some of the unwanted biases in some cases. Here are some references, and thank you so much for the talk, for the attention. I think there's a question as well. Can you talk about more about its application in our life? For the last work, so the main problem that we are solving here is how can we have more fair outcomes? So there are tons of applications, like you have a job screening system. You want to see which candidates you want to interview or not. So your model needs to be fair, right? But you also want this fairness to be done. You want your mitigating bias to be done in an interpretable fashion. You just don't want a black box model. If something is causing unfairness, I want to know which features are causing them, if they are informative or not. And if they are not informative and they're problematic, then let's remove it. So in terms of application, there are tons of, again, high-stake decision, maybe like parole decisions, or again, this job hiring scenario that we need to have to achieve fairness on the outcomes according to different fairness metrics, statistical parity, equality of opportunity. But you want to know what is exactly the reason and how can I mitigate the bias in an interpretable fashion. Because again, you need to audit these systems. If it's just a black box model, you are in trouble because you don't know what exactly the model is doing. Whereas in this case, you know, this feature is problematic, I'm gonna remove it. Maybe the practitioner is gonna say, no, I need this feature. Whereas if the model is not interpretable, you cannot have a control on such cases. Yes.
Thank you very much. Thank you for Nina's great talk. Here, the talk have many intriguing questions. Audience are very interested in your talk. This is really wonderful. Let's thank again for Nina's giving us her talk. We sincerely appreciate it. In the future, hopefully, you could visit us physically in Tokyo. I think the pandemic will end very soon, so we could meet physically in the near future. Thank you again for Nina's talk. This is the end of our today's seminar.
Thank you.